Ever wondered how operating systems manage memory, particularly how they allocate frames? Well, that's exactly what we're here to explore today. Frame allocation is a critical aspect of memory management in operating systems, especially when it comes to virtual memory. It's all about deciding how many and which physical memory frames, the smallest fixed-size blocks of memory, are given to each process or to the system itself. It's a task that needs to be handled with great efficiency, as it plays a crucial role in optimizing system performance and utilizing available memory resources. By understanding the basic concepts and strategies of frame allocation, we can better comprehend how our computers keep things running smoothly. So buckle up, because we're about to dive into the fascinating world of frame allocation. In the next few minutes, we will demystify the concept of frame allocation and how it contributes to optimal system performance. First off, let's understand the basic building blocks, frames and pages. Now, when we talk about memory in a computer system, we're dealing with two types: physical memory and logical memory. Physical memory is the actual RAM that your computer has, and it's divided into small fixed-size blocks called frames. Think of these frames as the actual empty bookshelves in a library, waiting to be filled with books. On the other hand, logical memory refers to the memory that a program perceives it has for its use. It's divided into pages, which are the same size as frames. These pages are like the books that need to be placed on the bookshelves. So how do we fit these books onto the shelves? That's where the operating system comes in. It acts as the librarian, deciding where each book or page goes on the bookshelves or frames. Now, it's important to note that the size of a frame and a page is typically the same, and it's determined by the hardware. This makes it easier for the operating system to manage memory, as it simply needs to match each page with a corresponding frame. However, not all pages are loaded into frames at once. Only the ones that the program needs to use immediately are loaded. This is because physical memory is a limited resource, and we want to make the most efficient use of it. So the operating system only loads the pages that are currently needed, leaving the rest on the hard disk. When a program needs to access a page that's not currently in a frame, a page fault occurs, and the operating system has to load that page into a frame. This is a bit like a librarian having to fetch a book from the storeroom because it's not currently on the shelves. So you see, frames and pages are key components of memory management in any operating system. They help to make the most efficient use of physical memory, while giving programs the illusion of having a large amount of memory to work with. Now that we know what frames and pages are, let's discuss the page table. The page table is essentially a map that each process has, which links its pages to frames of physical memory. Think of it like a translator, deciphering where each page of a process should reside in the physical memory's frames. When a page is referenced by a process, the operating system doesn't have to embark on a wild goose chase. Instead, it consults the page table, which provides the exact location of the corresponding frame in physical memory. This is akin to using a well-detailed map when navigating a city. You don't have to wander aimlessly because the map guides you to your destination. In the same vein, the page table efficiently guides the operating system to the correct frame for each page reference. The page table therefore acts as a vital translator in the process of frame allocation. With the basics out of the way, let's delve into the strategies used for frame allocation. These strategies fall under two broad categories: static and dynamic allocation methods. Static allocation is the simpler of the two. It involves a fixed division of frames among the processes. The first method under static allocation is equal allocation. As the name suggests, each process gets an equal number of frames. Simple, right? But it can become inefficient if processes have widely different memory needs. Imagine allocating the same amount of space to a lightweight chat program and a graphics-intensive video game. Not the best use of resources, is it? This brings us to the second method, proportional allocation. Here, the frames are allocated based on the size of each process. It's like giving each process a piece of the memory pie proportional to their appetite. A larger process gets more frames than a smaller one. Moving on to dynamic allocation, this is where things get a little more interesting. Dynamic allocation adjusts the number of frames allocated to each process based on its actual needs and performance metrics. It's like a responsive system that changes according to the evolving needs of the processors. One such dynamic method is the working set model. Here, frames are allocated based on the working set of each process. Think of the working set as the set of pages that the process is currently using actively. By keeping all these pages in memory, the method aims to minimize page faults and keep the system running smoothly. The second dynamic method is based on page fault frequency. This strategy ensures that the page fault frequency stays within acceptable bounds. If a process starts causing too many page faults, it's given more frames. If it's not causing many page faults, some of its frames are taken away. It's like a balancing act, ensuring that no process hogs too much memory, while also avoiding unnecessary page faults. These strategies ensure that frames are allocated efficiently, keeping in mind the needs of each process. However, it's important to remember that these are not one-size-fits-all solutions. The choice of strategy would depend on several factors, such as the size and behavior of the processes, the system load, and the memory pressure. In the end, the goal of frame allocation is to optimize both system performance and the utilization of available memory resources. It's a complex task, but when done right, it can make a world of difference in how smoothly your system runs. So the next time you're multitasking on your device, spare a thought for the clever frame allocation strategies working behind the scenes. But what factors influence frame allocation? Let's find out. When it comes to frame allocation, a few key factors come into play. First off, we have the size and behavior of the process. Larger processes, as you might imagine, typically require more frames. But it's not just about size, behavior matters too. For example, processes that are heavily involved in input-output operations might actually need fewer frames for code or data compared to those performing intensive computations. So the operating system needs to take both the size and the behavior of each process into account when allocating frames. Next up is system load. When the system is under heavy load, it may be necessary to reallocate frames among processes dynamically. This isn't about playing favorites, it's about ensuring that the system continues to operate smoothly. If one process is monopolizing frames, it could slow down the entire system. So in times of high stress, the operating system might step in and redistribute frames to keep everything humming along. And finally, we have memory pressure. If the physical memory is highly utilized, the operating system may need to apply stricter controls on frame allocation. Why? Well, it's all about preventing thrashing. If too many pages are being loaded and unloaded from memory in quick succession, it can cause the system to slow down, a phenomenon known as thrashing. By keeping a close eye on memory pressure and adjusting frame allocation accordingly, the operating system can help to prevent this from happening. So there you have it. Process size and behavior, system load, and memory pressure. These are the key factors that influence how frames are allocated in an operating system. And while it might sound complicated, remember that it's all about balance. The operating system needs to make sure that every process has enough frames to operate efficiently without letting any one process hog all the resources. These factors play a crucial role in determining how frames are allocated in an operating system. Lastly, let's talk about some techniques used in conjunction with frame allocation. When the operating system needs to free up a frame, it has two options. It can either allow a process to replace one of its own frames, which we call local replacement, or it can replace any frame in the system, known as global replacement. While global replacement can optimize overall memory use, it can potentially impact the performance of other processes. Another technique involves the adjustment of multiprogramming levels. In systems where the number of concurrent processes can be controlled, the operating system might increase or decrease the degree of multiprogramming. This is based on current memory usage and performance metrics. So if memory resources are running low, the system might reduce the number of processes. Conversely, if there's plenty of memory to go around, more processes might be allowed to run concurrently. These techniques further refine the process of frame allocation, ensuring efficient memory management.